Okay, this meeting is being recorded. All right, let's begin. So, this is the lesson I think for today and Monday, maybe Tuesday. I'm gonna have to look at my calendar, but we are definitely on track. It's getting pretty dark out there, isn't it? Rain's coming. All right, why is my clicker not working? There we go. Okay. So section 3 is solids and liquids. We're going to do liquids first. Remember that gases do not have bonds between the molecules, those intermolecular forces. So they are free to go wherever. Gases can fill out an entire container because there's nothing withholding their movement or their range. Liquids and solids are bound to each other. They are not free to go wherever they want. They are all bonded together. So we're going to start, mostly today, we're going to do liquids. We're not going to do solids at all. So when we did gases, we did the kinetic molecular theory. That was developed to try to explain gases, but it can also explain the nature of liquids and solids too. Remember that the particles in a gas are moving the fastest. They have the greatest kinetic energy. Solids and liquids are moving too. If you guys can look at me for a second, I'm going to try to visualize it for you. This is a gas. All that crazy movement, a lot of kinetic energy. Here's a liquid. Then here's a solid. And then the only time that everything will be completely stopped is at the temperature called absolute zero. That is 0 Kelvin. In Celsius, that is negative 273 degrees Fahrenheit, or Celsius, negative 273. Let me see if I can convert that to Fahrenheit. I think it's like 4 something. 273 times 1.8 plus 32. It's negative 459 degrees Fahrenheit. That's when things will stop moving. If you were exposed to that temperature, you would flash freeze just like that. Yes. Nothing can get colder than 0 Kelvin. It's been, I think they've come really close in the lab, but it's the coldest, darkest regions of space. If you were to float around in space, you would just flash freeze. Now, consider the forces of attraction in the liquid itself. Remember that you have what do you call the bonds that are in between particles? So if mass is a particle, Kendall is a particle, Colby is a particle, and they were all bonded together. What type of bond would that be? Intermolecular. What do you call the forces that are holding Colby together in one piece? Or Kendall, or mass? Intramolecular. Yes. Remember that the stronger those forces are, the less you can move. If you're wearing handcuffs like this, and the handcuffs are really tight, you can't even do this. Like your wrists are stuck. But if there's a long chain between your 2 handcuffs, you can do this. The bonds are not as strong. So if the bonds are weaker, the particles can move more. If the bonds are stronger, the particles can move less. Solids have stronger bonds than liquids, and liquids have stronger bonds than gases because gases don't have any bonds. All right, so a few things to consider and to remember about a liquid. A liquid can take the shape of this container on one condition. I'm going to borrow your phone. There has to be enough of the liquid itself to take on the shape of the container. Notice that everything above here, above Kendall's water, is a gas. Gas can fill this entire container because gas is unbound. It can fill it all out. Liquid will fill out the shape of a container only if you have enough liquid. But if I've, I don't think I have it in here. No. But if I had an empty bottle, that bottle is filled with gas, and the gas is taking on the shape of the container because there's nothing restraining the gas from going where it wants to go. A volume is not fixed. It doesn't change when there isn't any addition or reduction of the liquid. So liquids will be able to assume the volume, whether it's shaped like a bottle, shaped like a balloon, shaped like a bathtub. You just have to have enough of the liquid because liquid tends not to, I guess you could say, defy gravity. Gases can go where they go. There's nothing stopping the movement. But also keep this in mind. Which way does hot gas go? Does it rise or does it sink? It rises. Hot air rises. Cold air sinks. When you are taking a shower, if you have the hot water's running, the first part of your mirror you get fogged up is the top, because that's where the hot air goes. And then eventually the whole bathroom will fill with steam and your whole mirror is fogged. Individual particles in a liquid do not have a fixed position in a liquid. They can move around. I want you all to be clear about that. Liquids move around, but there is a limit because they are bonded to other liquid particles. Gases don't have a limit. They go wherever they want. Or I shouldn't say like that makes it sound like they have a mind. They can go where they can. There's no restriction. Attractive forces are stronger in a liquid than they are in a gas. There are no attractive forces in a gas. Remember them. Kind of like a trick question. What are the attractive forces in a gas? There are none. You have to slow down a gas. In order to slow it down, to get them to bond, you have to cool it down. So the forces in a liquid are weaker than a gas, or stronger than a gas, actually, but they're weaker than a solid. Another thing you're going to see either today or Monday is don't get the words liquid and fluid confused. A fluid, this is on your semester exam review, a fluid is something that can flow. Gas, like the gaseous state, not like gasoline. Gas can flow. When I do this, gas is flowing. Liquids can do that too. Solids cannot. So a liquid and a gas are considered fluids. Keep that in mind. Don't just strictly think that liquid is fluid and fluid is liquid. That's wrong. Okay, let's go to density and compression. Let me ask you guys before I reveal any others. What has more space between the particles? A gas or a liquid? Bingo. So which of the two can be compressed more? Exactly. There is not a lot of space between liquid particles. They are more dense. So over here, on this slide, you have a chamber with a plunger. A plunger is something you push down. Look at the difference between the first image and the second image over here on the gas. Everybody look up here. All these little blue particles are gas particles. This plunger is going to push down on them. Look at the difference in the volume. You guys have a lot of space between you. I could probably cram all of you behind my desk out there if I really tried. I could put you all back there. You would be really tightly packed. But I bet you we could get it done because you have so much space between you. When we have those lockdown drills, all of you spread out are all crammed in the back of the room. Liquids, it's a different story. They are already densely packed. So you really can't compress them much more than how they are. Vapor typically just means that something that was a liquid has been vaporized. Yeah. That's what condensation is called. No, not necessarily. Turning a gas into a liquid involves two things: pressure and temperature. If you apply enough pressure, you can force the gas particles to come together as a liquid. Think about a propane tank. You fill it up, it's a gas. But when it comes out, or you fill it up with a liquid, it comes out as gas. It's decompression. So that's what it means. They're compressing or decompressing. Press them out or force them together. So if you have an instrument like this, you're applying enough pressure, you can force those gas particles close enough to each other where they actually start to contract because they're so close. They have limited room to roam. The higher the density of liquids is due to their intermolecular forces. Basically, guys, liquid particles are bonded very close to each other. If Max was a gas particle and I'm a gas particle, we're going to be separated like this, far away, not even bonded. But if we're a liquid, it's like this. If we're a solid, it's like this. We're getting closer and closer. Liquids are pretty much incompressible. You really can't push them together any closer than what they are. You might be able to do just a little bit, but nothing significant. You're not going to be able to make a significant compression into liquids. They're already condensed. I mean, that's what the word condensation means. When you were in second grade, your second grade teacher talks about the water cycle. All right, kids, it evaporates down to the ground, or it precipitates down to the ground, it evaporates up to the sky, then it condensates. That's where liquid becomes, it comes from a gas. Condensation, it condenses. You're bringing them together. Liquids are already tightly packed, unlike gases. You're not going to have much luck getting them even more squeezed in together. Questions? All right. So, you heard Arshon talk about non-Newtonian fluids. The heck does that mean? Non-Newtonian is referring to Isaac Newton, one of the founders of modern day physics. Non-Newtonian fluids are liquids that seem to contradict Isaac Newton's laws of physics, where it looks like a liquid, but for just a fleeting moment, it can behave like a solid. Now, I have a video from the Ellen show that's an ancient video, it's got to be from 2004 or something, to demonstrate this. And what you see up here, you see this person is running on water. It's not actually water. It's cornstarch in water. And what happens is cornstarch in water, it behaves like a liquid, but when you impact it, like you punch it or you stomp on it, all the molecules pack in really quick, and it is for just a millisecond, behaves like a solid. But you have to continue to add pressure to it, or else you're going to sink it. So if you see that person running, if they just stood still, they're going to sink. You have to keep running and applying pressure. Yeah. I'm sure there's some out there. I can't think of any right now. There's got to be some viscous material out there, maybe the earth. Yeah. The Dead Sea just has a lot of salt. That's all. So nothing is too salt. This salinity is high. All right. So, as I was saying a few minutes ago, do not get the words liquid and fluid together, because a gas is considered a fluid too. That is on your second semester review. So which of the following, which states of matter are fluids? If you just say liquid, you're wrong. Gases as well. The reason why is because they can flow and they can diffuse. Liquids usually diffuse more slowly because they have bonds. They have those intermolecular forces. Gases don't have that. If you try to deflate a balloon, it takes you a second. If you try to get all the water out of the balloon, it's going to take longer than a second, because all that water is bonded and they all have to leave together. Liquids are less fluid than gases. And when I say fluid, it means it's flowing. When we say that 2020 was a very fluid situation, a lot of change going on, a lot of moving parts. That's what they mean by fluid. It can move. So if I say, Max, what are we doing this weekend? I don't know. It's fluid. It means it's changing. There's a lot of things that can move. The schedule can change. It can move around. That's what we mean by that expression. So imagine you have a water leak versus a gas leak in your kitchen. Which one is going to fill out your kitchen first? Yeah. Gases are unrestrained. You're gonna smell that real quick. And plus, nothing is going to stop the gases from rising and falling and filling out your kitchen. If you have a water leak, it's going to be the floor first, and then it's going to rise, because it's bonded, so it's heavy, and so it has to bind like that. Well, I don't know what I'm trying to say there. The water will likely remain on the floor unless it's a ton of water. Will the gas fill the volume of the room? Yes, it will. All right, so given this image, I'm going to pause and I'm going to show you this Ellen show clip with non-Newtonian fluids. So if you're listening at home, go to YouTube and type in Ellen non-Newtonian, Newtonian, New. So that's what we're going to do here. I'm going to escape out of this PowerPoint real quick. Let's pause this. All right, so let's get back to the slide we were on. Okay, so we just did the little non-Newtonian fluid, but let's not glorify the exception rule. Here's another vocab term. Wasn't this just on your quiz? Viscosity? No? Oh, well, there you go. This is like honey or maple syrup. It is resisting flow. When I was in school, I always got confused. Okay, if something like this, when I say it's highly viscous or it doesn't have viscosity, remember that the definition of viscosity is resistance to flow. Is this resisting flow? Yes. So you would say that is highly viscous. That this is a viscous substance. Viscosity is a measure of resistance of a liquid to flow. So this honey up on the screen would be a viscous substance. The reason why you can get a liquid to be like this when it's really cool or the molecules are very closely bonded to each other. It's going to flow, but it's kind of sort of resembling a solid, but not entirely. The particles of liquid are close enough for attractive forces to slow their movement as they flow past one another. From what? Was that in the book? So if a liquid is to be viscous, it really just depends on the type of intermolecular forces that are present and how close the particles are, how large the particles are, the temperature. Obviously, would be more likely in cooler environments. I would tell you that cold honey is going to flow a lot slower than warm honey. When I'm making dinner and I have to put some olive oil in the pan, warm olive oil flows a whole lot better than cold olive oil. So temperature is certainly a big component. So is the size and the shape of the molecules, the types of forces that hold them together. If you didn't see viscosity in your vocab, you'll likely see that in your test. You know, if you have a sore throat, honey is a really good pain reliever. You know, like laryngitis. All right, here we go. Do a little karaoke on that thing. Eric, if you were in a 100-foot pool and I told you you had karaoke across, would you do it? For the rest of the round. Okay. Remember that the stronger the forces, the less motion there is, which means less kinetic energy. Size and shape of the particles also affects viscosity. If you had two liquids and one liquid had larger particles than the other, the liquids with larger particles will likely be more viscous because they're going to just be slower to move. Here's another image of viscous versus non-viscous. Air gel is viscous, water from the tap is not viscous. Viscosity decreases with temperature. You can prove that just by putting honey in the fridge versus honey that you store in the pantry. The refrigerated honey would flow much slower because there's less kinetic energy, which means the bonds are strong. When you pour cooking oil on a cold skillet, as I was mentioning, when it's cold, the oil is not going to flow very well. But once you heat it up, it's going to start to flow much better. You can cover the whole surface of your skillet. So when I put the olive oil on the stove, on the skillet, I let the skillet warm up for maybe 5 minutes, and I pick up the handle of the skillet and tilt it back and forth so it covers the whole skillet. That's because the heat has loosened up the molecules, and the whole liquid is more viscous or less viscous. And then the last one we'll get to today is surface tension. This insect is called a water strider. Look at how it's actually pushing into the water. Water is sticky. I've never heard it referred to like it, but because of the hydrogen bonds, it's actually pretty sticky. And when you have a force pushing down on the water, like gravity, that actually strengthens the bonds and their resiliency, and they're going to stick together. Now, as I said yesterday, everything does have a breaking point. If you throw a rock or your dog or you into the water, the surface will break. But something like a water strider is light enough to stride along the surface of the water without actually penetrating the surface. That is because water has a very high surface tension. As forces like gravity or the mass of a little animal are pushed down on the water, it actually strengthens the bond between the water, or any liquid for that matter. Water is just a really good example. And that's because of the bond, the intermolecular bond between the water, or whatever liquid that would be. All right, we will stop right there.